Assalamualaikum and good morning. For this group assignment, the given topic for our group, which is combined for two topics, A. Triple integral in cylindrical coordinate, and B. Divergence theorem that will be focuses on Green's theorem. Now, let me introduce our group member consists of 4 people. Firstly, me, Samirah binti Zaki. Secondly, Nurul Hidayah binti Johar. Thirdly, Nur Izzati binti Mohd Kamil. And lastly, Nur Amisyah binti Saiful Nizam. Next, for the part A, will be discussed by Izzati and Amisyah, followed by Hidayah and I will be explained for part B.
I will show how to solve the triple integral in cylindrical coordinates problem. So, question 1, from the question, we can see that the diameter of the product is 6 cm in form of the cylinder. Then, the cylinder was cut by a line with equation z equal to negative 1 over 2y plus 8. So, from the design that provided to Mr. Rahman, we convert into the 3D graph, and this is the shape of the graph. So, from the graph previously, as we see from the z-plane, we can see that the shape formed at the xy plane is a complete circle with the radius of 3. From these two graphs, we can determine the limit for x, y, and z. So from these two graphs, we can solve the triple integral of 2x squared plus y squared dv. As we see the surface from z-plane, we set the dz as the innermost limit, followed by y and x. So, as we see that at the y limit, this has a square root of 9 minus x squared, which will make the calculation become complicated. So, we convert from polar coordinate into the cylindrical coordinate, which is in triple integrate of 2r squared dz r dr d theta, and the limit was set from the graph, and the calculation was continued. So by substitute the upper limit and the lower limit into the function after we integrate, we can obtain the final answer, which is 648 pi.
Next, to find the volume by using the triple integral of cylindrical coordinate, must remember that x equal to r cos theta and y equal to r sin theta. So, from the equation z equal to negative half y plus 8, so it will become negative half r sin theta plus 8. From the graph that we sketch, the limit for dz is 0 to negative half r sin theta plus 8, since it starts from 0 to the height of cylinder. For dr, the limit is from 0 to 3 for the radius, and for the d theta, the limit starts from 0 to 2 pi because we're going to integrate all the way around the cylinder. So now we put in what we have left. So we have r dz dr d theta, and now we integrate start from r dz. So we integrate r dz, we get rz evaluate from 0 to negative half r sin theta plus 8. And then we still have dr d theta, so we put the limit of integration into the equation. We get negative half r squared sin theta plus 8r dr d theta. After that, we integrate over dr with limit 0 to 3. We get r cubed sin theta plus 4r squared, and we put the limit into the equation. We get 36 minus with bracket minus 9 over 2 sin theta d theta. Last, we integrate d theta, and we will get 36 theta plus 9 over 2 cos theta with limit 0 to 2 pi. So the final answer for V is 72 pi.
Here I'm gonna explain about how to solve the problems of fluid mechanics by using divergence theorem and which Green theorems. Here are the problems that we need to find the velocity at point. Here are the problems. We need to find the velocity at point 2. To get the velocity at point 2, we use Reynolds transport theorem that we get from derivations of Green's theorem concept. Green theorem can be only used for vector fields in 2 dimensions. The use of Green theorem to calculate the area of region. The given data is diameter at point 1 and point 2 is 5 cm and 7 cm respectively. For the velocity at point 1 given 3 meter per second, and for the flow rate at point 3 is given 0.01 meter cube per second. So we assume that the height in the tank water is constant because it's steady flow. So to take out the integral, we also assume that the density at point 1, point 2 and point 3 is also same, as it will be in incompressible fluid. Here are the Reynolds transport theorem formula. So B big is for the mass extensive property. So change the mass of extensive property of the system is per respect to time is equal to 0. So you also assume that in mass of control volume does not change with respect time is equal to 0. And we do have 3 control surface, so we put as C1, CS1, CS2 and CS3, which is if we have flow in, the Vn will be negative. If we have flow out, the Vn will be positive. So as we say just now, the density at point 1, point 2 and point 3 is constant, as it will be in a compressible fluid. So then it left only velocity and the area. So we derive the velocity and area. To get velocity at point 2, we get 4.13 meter per second.
For part B, the application of Green's theorem that we use in this video is Reynolds transport theorem. From the question given, water flow, density is constant, D1 equal to 10 cm, D2 equal to 15 cm, V1 equal to 10 cm per second, and it's stated that the system in steady flow. The question asks us to find V2. From this diagram, the yellow one is called system. We considered a certain amount of fluid in this system. And the outer blue one is called control volume. It is a fixed place. So, here in this system, at some time, both the system and the control volume take up the same space. The V is an extensive property of the system with respect to time. This equation says that the time rate of change of some extensive property here of the system is equal to the rate of change of the property as it flows through the control volume with respect to time. When system is in steady flow, the rate of change of the property as it flows through the control volume with respect to time equal to 0. And then we put 0 into the equation and we'll solve the equation as shown. Or we can use rho 1 V1 A1 equal to rho 2 V2 A2. And then we find V2. We insert the value given. And then the final answer is 4.44 cm per second.